Ladies and gentlemen, dear colleagues and honored guests, welcome to this special lecture as part of the Boğaziçi lecture series. So my name is Hasan Umut. I'm an assistant professor in the history department here at Boğaziçi University, specializing in the history of astronomy and modern science. So it's a great honor to have with us today Professor Jamil Ragep from McGill University. So Professor Ragep is widely recognized for his important contributions to the history of astronomy, particularly within the context of Islamic civilization. His scholarship is especially meaningful and remarkable in helping us contextualize the scientific achievements of the Muslim world within the broader global history of science. So we are very excited to hear from him today and learn more about the fascinating exchanges of knowledge that shape the history of science. So I don't want to take up much of your time, as we are all eager to hear Professor Ragep's lecture. But before we begin, I would like to invite our president, the president of Boğaziçi University, Professor Mehmet Naci İnci, to deliver his welcoming remarks. Hocam buyurun.
Distinguished guests, esteemed colleagues, very dear students and friends, welcome to the Boğaziçi lecture. It is a great pleasure to see you all here today as we come together to explore an important topic and share ideas. First of all, I would like to express my heartfelt thanks to our esteemed guest speaker, Professor Jamil Ragep from McGill University. We are truly honored to welcome one of the leading scholars in the history of science, particularly in the area of Islamic civilization. Professor Ragep's work has deepened our understanding of how scientific ideas were shared and developed across cultures in the pre-modern world. His research has shed light on the scientific achievements of Muslim societies and their global impact, including their influence on the Copernican system. It is a privilege to have him with us today to deliver his lecture, Tales of Transmission, Scientific Exchanges in the Pre-Modern World. I would also like to extend my gratitude to Turkish Academy of Science, TÜBA, and its president, Professor Muzaffer Şeker, for their invaluable support and collaboration in organizing this event. Boğaziçi Lecture Series is a vital part of our university's mission. It brings together leading academics, intellectuals, and policymakers to exchange ideas and share knowledge that deepens our understanding of the past and present, while guiding our vision for the future. These lectures reflect Boğaziçi University's commitment to fostering dialogue and interdisciplinary thinking. As a scientist specialized in the field of quantum optics, I have always been fascinated by the history of science. Studying the history of scientific ideas shows us how science has evolved over time, shaping societies, perspectives, and even cultures. Looking to the past provides us with valuable insights that help inform and guide the decisions we make for the future. I am reminded of my late colleague and dear friend, Professor John Freely, who shared a deep passion for the history of science. During more than 20 years of working together in physics department, sharing the same office with Professor John Freely next to my lab, I witnessed his incredible dedication to teaching and writing about this field. John Freely's work, which continues to inspire us through his books and contributions, has left a lasting legacy at Boğaziçi University. At our university, we are proud to offer courses in the history of science, particularly in our history and physics departments. These courses complement one another, helping students understand science not just as a collection of facts, but as a dynamic and evolving process. As president of this beautiful university, I am committed to expanding these offerings and providing more resources for students and researchers who want to explore into this fascinating field. The history of science is also deeply embedded in Boğaziçi University's institutional legacy. Our Kandilli Observatory and Earthquake Research Institute, established in the 1860s and part of our university since the 1980s, was the first modern observatory in the Ottoman Empire. Today, Kandilli is one of the leading research centers in Turkey and the surrounding region, particularly in the area of earthquake sciences. The Kandilli Institute also holds a remarkable collection of manuscripts in mathematics and astronomy written in Arabic, Turkish, and Persian, along with historical instruments together located in Kandilli campus. These resources highlight the rich scientific traditions of this region and offer significant opportunities for researchers. Boğaziçi University's roots in science education go back to the Robert College in the 1860s. This long tradition of excellence in science and education has shaped our university's identity. As we look to the future, I am excited to support studies that examine the history of science at both Robert College and Boğaziçi University. I believe it is time for us to document our own history through the lens of the history of science. In this respect, to our students, faculty, and researchers, I encourage you all to explore this important field. Studying the history of science not only helps us better understand and honor our past, but also inspires new ideas and discoveries that can shape our future. Boğaziçi University stands ready to support this work and foster collaborations to advance this area of study. In closing, I want to thank Professor Jamil Ragep once again for being here with us today and for sharing his invaluable expertise. His lecture will provide important insights into the exchange of scientific ideas in the pre-modern world, a topic that aligns closely with Boğaziçi University's mission and values. Finally, I would like to thank all of you for attending and for contributing to the vibrant intellectual life of our university. I hope you find today's lecture both inspiring and thought-provoking. Thank you.
I would like to thank Professor Nacinci for his warm welcoming speech. and for emphasizing Boğaziçi University's strong commitment to the study of the history of science. So it's indeed inspiring to see how our university continues to support and engage with this important field of research. So before we begin, I would like to take a moment to briefly introduce our distinguished speaker, Professor Jamil Ragep. So Professor Ragep was born in West Virginia in the United States and is currently an emeritus professor at McGill University in Montreal, Canada. So he graduated from the University of Michigan with degrees in anthropology and Near Eastern studies, and later earned a PhD in the history of science from Harvard University. From 1992 to 2006, he was a professor in the Department of the History of Science at the University of Oklahoma, one of the prestigious programs in the field in the United States. So in 2006, he joined the Institute of Islamic Studies at McGill, where he held a Canada Research Chair until 2020. So this chair is one of the most prestigious awards given by the government of Canada to attract leading academics to the country. Also, he has received a lot of prizes and awards, including Turkish Academy of Sciences International Scholar Award. Professor Ragep is a leading scholar in the history of science in Islam, and his work has had a profound impact on our understanding of the transmission of scientific knowledge across cultures. He has co-edited works on the exchange of scientific ideas between cultures and on water resources in the Middle East. So in collaboration with the Max Planck Institute for the History of Science in Berlin and later with Istanbul Medeniyet University, Professor Ragep has been leading the Islamic Scientific Manuscripts Initiative, ISMI, an ongoing international effort to catalog and provide access to Islamic manuscripts in the exact sciences. So he has raised many students, including myself. So his most recent research focuses on the Islamic background to Copernicus, the astronomical works of Nasreddin Tusi, a famous 13th century astronomer and scholar, the philosophy of Qutbuddin Shirazi, another important figure in Islamic intellectual history, and the reception of Ali Kushti's astronomical ideas. So it is with great pleasure that I now invite you all to join me in welcoming Professor Jamil Ragep to deliver today's lecture. Please, Professor Ragep, the floor is yours.
What do I press? Well, thank you both for the very nice introductions, and I want to thank President Mehmet Naji Enji and Dean Hassan Umut for inviting me to speak today. And it's always nice to hear encouraging words from the president of a university about history of science, a field that sometimes doesn't get all the attention it should. So it's wonderful to hear your very kind remarks today. It's actually a kind of homecoming for me and my wife Sally to come back to Boğaziçi, because we live just down the road in Rumeli Hisar a few years back, I'll put it that way. And we had a wonderful time sort of walking through your campus and maybe occasionally taking advantage of your sports facilities when we could sneak in. And so it is a kind of homecoming for us, and it's always wonderful to be in Istanbul. The history of science provides a significant way to trace intercultural transmission. In fact, one might consider it our most precise way to document such exchange. Today, I would like to tell a few stories, and it's actually just a very few because there are so many more one could tell, about the transmission of science in the pre-modern world, and try to draw some lessons from those intercultural exchanges that were, in retrospect, so important for the rise of modern science. I also will be pointing to the historiographical tension that sometimes exists between telling the story of transmission and telling the story or emphasizing cultural difference. Let me see. The gold standard for transmission in the history of astronomy is arguably Hipparchus's value for the mean synodic month as reported by Ptolemy, namely 21 days, 31 minutes, 50 seconds, 8/3, and 20/4. So let me explain that a little bit. The number you see up there in days is in sexagesimal, in the sexagesimal system that was invented by the Babylonians a long time back, but we still use today. Every time we say there are 60 seconds in a minute and 60 minutes in an hour, we're using the sexagesimal system of the Babylonians. What this number means, and it's a very precise number, I should say, is that it's 29 days, 31 over 60, and then 50 over 60 squared, plus 8 over 60 to the third power, plus 20 over 60 to the fourth power. So it's precise. Now, as I said, this number is reported in Ptolemy's Almagest. Ptolemy lived in the 2nd century of the Common Era, and he attributes it to observations made by Hipparchus, who lived in the 2nd century, BCE. Okay, is that better? Okay. Now, a synodic month is simply the time between one phase of the moon to the next. So, for example, from new moon to new moon. And it's synodic because it's based on the moon's position with respect to the sun. So, that, I hope, explains part of what's on this slide. Let me try to go on to the rest of it. Once the Jesuit scholar Franz Kugler demonstrated in the 1890s that this value came from what is now known as Babylonian System B, and Babylonian System B is, let's see, does this work? Yeah. Is illustrated here on this cuneiform tablet. The argument for Greek knowledge in use of Babylonian astronomy, at least its parameters, became incontestable. Also incontestable was that Hipparchus, despite what is reported by Ptolemy, did not make a recalculation using new observations. But why can we conclude this? This again goes back to how history of science helps in understanding intercultural exchange. Would anyone seriously contest that two values to the fourth sexagesimal place is coincidence? Now, solidifying the claim of transmission was a chance discovery in 1988 by Otto Neugebauer, the renowned historian of ancient astronomy. He was able to show the very complex lunar theory of Babylonian System B had been translated into Greek. This is this papyrus here, the Greek papyrus that was discovered relatively recently. But besides the transmission of some numbers and techniques, are there larger implications of these discoveries? George Sarton, the 20th century Belgian historian who found an academic home at Harvard and is arguably the founder of the modern discipline of the history of science, thank you, took Babylonian science to be mostly recipes and not really science at all. For him, real science demanded an underlying philosophy of science based on axioms, postulates, and a logic-based notion of truth. Others, notably Neugebauer and his students and grand students, have taken a different position, namely that the Babylonian insistence on precision, indeed their discovery of mathematical astronomy, is their distinct and exceptional contribution to our scientific traditions. Now, let's delve a bit further into this and ask where, historically, a philosophically based science, like that advocated by Sarton, might have led. Now, our best evidence comes from Plato and Aristotle and their discussions of astronomy. In the Republic, Plato has his protagonist, Socrates, say the following: "The real astronomer will feel that the heavens and all that is in it has been constructed with the utmost beauty attainable in such work. But don't you agree that he would think it absurd to expect such objects, corporeal and visible as they are, to be forever invariant and to be absolutely undeviating, and to strive to determine their truth by every possible means? Instead, it is by means of problems, then, that we shall proceed in astronomy in the same way as we do in geometry, and we shall let the things in the heavens alone." Now, that's the end of the quote. Now, there's been a great deal of controversy about what Plato might have meant by letting alone or putting aside the visible things in the heavens. Is he advocating that we not do any astronomical observations? Without trying to unravel this thorny problem, which has bedeviled Plato's scholars since ancient times, it seems to be less controversial to examine what type of astronomy actually came out of Plato's academy. Here we have the testimony of no less than Aristotle, who gives a fairly extensive report of someone who studied at the academy, namely Eudoxus of Cnidos. Now, Eudoxus's system was based on uniformly rotating spheres with different axes of rotation. Here, this is here on the left. Oops. There. Here on the left. There. So these spheres are one inside the other, and all the spheres have a single center, namely the Earth. Now, what is interesting about this is that it adheres to several constraints that we know were critical to early Greek natural philosophy. Now, these constraints were perfect, uniform, spherical motion in the heavens and a single center for all motion. Such a system is philosophically coherent, but is a disaster as far as predicting what we actually see in the heavens. So maybe we should leave what we see in the heavens and go with theory. So this, for example, is what we might see over an 8-year period if we're looking at Venus's motion, and we can see that Venus performs these loops as it moves through its path through the sky. These loops represent retrograde motion, in other words, backwards motion with respect to the way it normally would be moving. Now, if we compare these loops with what Eudoxus' system predicts, we can see that Eudoxus' system predicts something called a hippopede, which is sort of a figure 8 on the surface of a sphere. Now, figure 8 is a beautiful figure, and a hippopede is wonderful. The problem is it's not anything like what we actually observe. So this then brings us to the issue of what a Platonic astronomy might have been versus what a Babylonian astronomy was. So it seems to me, excuse me, that Socrates, Plato, was advocating a system that does not reproduce what we see, but instead shows us what is the Platonic real form behind what we do see. Note that one can say that, this slide is a kind of ideal representation of that slide. Now, this all might work well in Plato's Academy, where, they were discussing this in a theoretical way, but there were other forces at work. After the conquests of Alexander the Great in the 4th century BCE and the political realignments that were brought about a multicultural Near East and Mediterranean, horoscopic, individualized astrology began to be practiced, an offshoot of Babylonian omen literature. But astrology demanded accurate observations, at least among those who were not charlatans. Here I think we can see the need for a different kind of astronomy than the one advocated by Socrates, Plato. And the modifications that are reported in the 3rd century BCE by such mathematicians and astronomers as Apollonius of Perga and Hipparchus of Rhodes testify to the drastic changes to the Eudoxan system, these changes being able to incorporate the great strides that had been made by precision-based Babylonian astronomy. So, not to get too deep into the weeds of astronomy, let me just say that what was introduced by people like Apollonius and Hipparchus were things called eccentrics, which are off-center. So immediately you see we're getting away from the Platonic ideal. It's still a sphere and it's still rotating uniformly, but it's not centered on the Earth anymore. And then to top that off, we have epicycles, which are inside the eccentrics, and they're not anywhere near the Earth either. So we have fairly drastic modifications, but one could still say, okay, we're adhering to spherical bodies in the heavens, and we're also adhering to uniform circular motion. So it's a kind of compromise, we might say. And if nothing else, it certainly works better than the Eudoxan system. If better, by better we mean that it actually predicts what we see in the sky. Now, the issue of precision is quite interesting in what it tells us about pre-modern cultures. As moderns, we take it for granted that precision is not only good, but natural. How else could we land on the moon, have computers that actually work, well, at least sometimes, or expect our Amazon shipment to get to us the same day? But history, as we have seen, teaches us a different lesson. Plato, and evidently his students, such as Eudoxus, defined precision differently than we do. They were mapping an ideal world that is only accessible to the mind and not the senses. On the other hand, the Babylonians, perhaps the only cultural group ever to do so, invented a precise science as a way to deal with critical social and political issues. For example, a predicted astronomical omen, such as a conjunction or eclipse, might foretell the death of a king. So the solution, have the king abdicate for a day, put a commoner in his place who is promptly killed, and then have the king return to the throne. But you need precision to make sure you're picking the right day, right? It was only a short step from this type of monarchical imperative for precision to its more populist offshoot, namely Hellenistic astrology. But even with this new broadly based astrological imperative for precision, the Platonic outlook did not completely go away. Ptolemy, in his mathematical syntaxis, which came to be known by its Arabized Greek name as the Almagest, claims all manner of observations, some of which are clearly bogus, but that's another story. But he warns us, this is Ptolemy, that comparing human constructions with divine ones is a fool's errand, seeming to echo Plato's unease with thinking that what we see is ultimate reality. In other words, our eyes can deceive us. Famous idea from Plato. But what happens when this type of thinking is translated and appropriated into another language and context? Here we can quote the 13th century Iranian Muslim polymath Nasiruddin Tusi, who is commenting on precisely this point that Ptolemy's making, his warning against comparing human and divine constructions. So what does Tusi say? He says, this whole thing that Ptolemy is saying, this is external to the discipline and is not persuasive. For it is necessary for a practitioner of this discipline to establish circles and bodies having uniform motions according to an order and arrangement, such that from all of them, meaning these circles and bodies, these various perceived motions will be constituted. Here we need to emphasize that it is the perceived motions that need to be modeled, and this is a refrain running throughout the history of Islamic astronomy. Even when the Greek texts, such as those of Ptolemy, were just beginning to appear in Arabic translation, there was quite a bit of skepticism about the observations that Ptolemy had claimed he had made. And to give you an idea of how they were looked at, this is from a 9th century critique of Ptolemy, and the author says, Ptolemy, in persuading himself that the period of the solar years should be taken according to points on the ecliptic, also persuaded himself as to the observations themselves, and did not in reality perform them. Coming from his imagination, this was of the greatest harm for what was described for the calculations. Some of you may be familiar with some modern work that Ptolemy was a fraud, that he made up his observations and so forth. But this shows you that this complaint about Ptolemy goes all the way back, over 1,000 years. So there was always some skepticism about his observations. But this is not mere rhetoric. From the 9th century on, we find Islamic astronomers focused, one might say obsessed, with better observations than the ones they inherited from the Greeks. And let me just go through a few quick examples. This is regarding the size of the Earth. We have a lot of different values. Wait, I have to do a little mechanical work here. Just give me 1 second. Okay. We have a lot of different values from the Greeks. We have a bunch of them listed there. Now, the thing that strikes me about this, I hope it strikes you as well, is how nice these numbers are. And they seem, you know, one could charitably say rounded to the nearest 1,000, 10,000, 100,000, whatever. So that's what we have with the Greeks. And I can't really tell you what these mean exactly because they're in something called stades. That's the length around a sports stadium. But sports stadiums were of different stades. So it's very difficult to know exactly what any of these numbers mean precisely. Now, in contrast, with the Caliph Ma'mun's astronomers in the 9th century, we can come up with a value, in other words, translating what they did, which was to go to the plain of Sinjar, which is in Iraq. Wait, is Sinjar in Iraq or Syria? Anyway, in upper Mesopotamia. And they did a survey going north and south, compared their values, and came up with a number that translates in modern terms to about 39,775 kilometers for the circumference of the Earth versus the actual value of 40,008. So pretty good. And El-Biruni had, a few centuries later, had another value close to it, but using a different method. This is called the dip of the horizon method. At any rate, we can see that with the Islamic astronomers, we can see that they came up with fairly good surveying techniques that led to good values for the circumference of the Earth. Another thing we can look at is the obliquity of the ecliptic, which is the tilt, in modern terms, the tilt of the Earth with respect to its motion around the sun. You'll see with Ptolemy, he's off quite a bit, 2351-20 versus 2340-40, which is what we can calculate he should have seen. He's off by about 11 minutes. But with El-Ma'mun's astronomers, and also with Ibn Sina, the famous philosopher, and Ibn Sina's associate, Al-Juzjani, we can see not only are they good to the nearest minute, but with Ibn Sina and Al-Juzjani, they're closing in on the seconds, which is fairly remarkable how precise these numbers were. And just to give you a quick notion of an interesting difference between the Islamic philosophers who followed Aristotle, Plato versus Plato, for example, Ibn Sina actually undertook an observing project in Isfahan. This is his observing instrument as it's been reconstructed in modern times, and perhaps this is the way he was able to get some of his precise numbers. Notice, though, that we have an Islamic philosopher very interested in observations. Now, these observations, of course, as I'm sure many of you are aware, extended to the creation of what Aidan Saili called an Islamic invention, and that was big science, the big science of observatories, starting with the great Mongol-built observatory in Azerbaijan and Maragha in the 13th century, and extending well into the 18th century in South Asia. You see some examples here in New Delhi. Of course, the Istanbul Observatory, which I'm sure I don't need to remind you of. And the thing about it is some of these instruments that were built are extraordinary. The instrument, the sextant, which is 1/6 of a circle, in Samarkand is 40 meters, has a 40-meter radius. 40 meters is enormous. This was used for meridian sightings of stars, we think. Anyway, but here again, we need to look beyond just the scientific details and note that change is occurring when we go from one cultural context into another. Exactly why that might be so in this case, the case of the Islamic world, is open to interpretation. Now, my own preliminary conclusion is that this has to do with the Islamic Abrahamic emphasis on the creation of the universe by a benevolent God. Here, understanding God and his creation becomes a kind of imperative, at least for those with the ability to understand. So, in the Quran, we read, well, I'll read the English and read the Arabic. God created the heavens and the earth in true harmony, and in that is a sign for the believers. This we find quoted a lot among scientists, and it's a kind of go-ahead to do their work. In other words, by studying nature, by studying the world around us, we're getting signs of God's existence. And this is also emphasized in a work by Sharif al-Jurjani, a philosopher scientist who died in 1413. This is from his commentary on E.G.'s Muwaqif work in Kalam, theology. Jurjani says, the characteristics of the celestial orbs in the earth and what they reveal of subtle wisdom and wondrous creation are things that overcome whoever apprehends them with awe, and facing him with the glory of their creator, prompt him to say, O Lord, thou hast not created this in vain. Of course, the last part is also from the Quran, from Al Imran. Anyway, we can compare this then with what we saw in Plato and the difference between taking the world as it is versus thinking there is a more perfect world behind what we actually see. Now, I think here we can see the way in which transmission is intertwined with the local. No one can deny that Islamic astronomy is in some deep sense a continuation of Greek astronomy. But by imprinting its local circumstances, one ends up with an astronomy that insists on both precision and an insistence on an astronomy that is both mathematically and physically consistent. To this we can add the new uses for astronomy, such as determining prayer times in the Qibla, which is the direction to the Kaaba and Mecca. And here we see a remarkable instrument that was designed to show the direction of the Kaaba from all of these cities that are in darker part on the brass. You can pick the city and then find the direction to Mecca. The interesting thing about this is that it's based on a very sophisticated mathematical technique of projection. Now, how am I doing for time? Okay. Okay, well, this is a little, so that's a little the heavier part of the talk. Maybe now we'll go to a little lighter part of the talk. Linguistic issues associated with the transmission of science. Now, linguistic issues are interesting because they allow us to see the strange ways in which words and phrases are transformed in unexpected ways, sometimes reflecting underlying aspects of a culture. For example, the chord function, which was standard in the Hellenistic world, was quite simple. You take a central angle, here A, and you associate it with a chord on inside the circle. Now, it's very simple and you can develop tables, but once you try to use chords for calculation, it is quite cumbersome. And so the Indians in pre-Islamic times decided not to use the chord function, but the half chord function. So they associated half the central angle, A divided by 2, with half the chord. Half the chord is, for all intents and purposes, what we would today call the sine of that angle. Now, you see, the nice thing about it, too, is it's taking advantage of a right angle, which is very, very good in the development of trigonometry. Now, in Sanskrit, this was called the Ardha Jya, or Java, or half chord, and this reached the Islamic world in the 8th century through contacts with Indian scientists who were told were part of a delegation that traveled to Baghdad. Now, this interaction between Indian mathematicians and early Greek Muslim mathematicians and astronomers eventually, quite quickly, led to a new field of knowledge called trigonometry, which actually, in the way we think of trigonometry, hadn't existed up to that time. So the sine function was the basis, and then Islamic mathematicians added cosine, tangent, and then their inverses, and then started studying relationships between them. So that's how we can then define the beginnings of trigonometry. Now, let's get back to the linguistic part. Now, this jia or java came into Arabic, and the person who was putting this into a text decided, well, there's no V in Arabic, so we'll just make it a B sound, so it's j-ba. And j-ba doesn't mean much, but if you add something in between and call it a jaib, then a jaib has meaning. It's an opening. Modern Arabic, it's a pocket, and so forth. So we go from Sanskrit into an Arabic word that has absolutely nothing to do with the Sanskrit, but it sounds a lot better than saying jub. You're now saying jaib, okay? Now, this was then translated. The Latin translators in the 12th century looked at this word and they saw jaib, and they said, well, how are we going to translate this? It's an opening. And so they came up with sinus. So from java to jaib, then it came to sinus, each step along the way being completely contingent on some translator or something. But that's why today we say sine and not say jaib or jub or java. Now, what it shows us is that the translator wanted to Latinize this concept, whereas the Arabic translator of the 8th century merely transcribed. So, you know, we have two different approaches here. One just transcription, one actually Latinizing it so that it makes sense to the Latin reader. Now, eventually, of course, the Arabic user transformed it also so that it make sense as an Arabic word. Now, there are many examples of this that, you know, let me move on. I think one of the things to keep in mind here is that there are different ways in which translation of transmitted words can occur. I've given you one example of domestication, where you go through different languages and each language wants to make it into something that sounds like their own language. But that's not always the case. For example, when you look up in the sky, there are stars named Deneb, Altair, and Vega. They were never Latinized. Those are, of course, Arabic names, Deneb, Ta'ir, and Waqa. So these then represent different ways of approaching language. And so transmission is never straightforward. Now, there are other examples. Let me go quickly through some of these. this is one of my favorite, the star Betelgeuse, which is in Orion. It's a red giant, we would call it today. And Ptolemy calls it the bright reddish star on the right shoulder of Orion, okay? And in the 10th century, in Abdurrahman as-Sufi's star list, it's translated almost verbatim the way Ptolemy described it. النير الذي على المنكب الأيمن وهو يضرب الحمر, reddish, and it has two names. We'll come to that in just a minute. Now, one of the names for this constellation is Al-Jabbar, and you see it up here, Al-Jabbar. Now, this means giant, and it's a nice translation since Orion was one of the giants in Greek mythology. But somewhat confusingly, it is sometimes referred to as Al-Jawzat. So it's Al-Jabbar, but then it's Al-Jawzat. Now, where does that come from? Al-Jawzat also is used for Gemini. So we have one name used both for Orion and the constellation Gemini, the ecliptic constellation. Now, and to make a convoluted story even more convoluted, Jawzat was the name of a pre-Islamic asterism or constellation used by the ancient Arabs for navigation and weather prognostication. So the problem is we have Gemini here, we have Orion here, and somewhere in this area there was this ancient constellation of the Arabs called Jawzat. So Jawzat is then now attached both to Gemini and to Orion. So it's a complete mess. And actually some of the commentators say this is a complete mess. And they then say, well, maybe we should just confine Jawzat to Gemini and call Orion Jabbar, but of course no one follows what people, reasonable comments like that. Now, we see here that the star Betelgeuse had two names, and both of them were associated not with Jabbar, but with Jawzat. So it probably goes back to the ancient Arabic name. So it's Mankab al-Jawzat or Yad al-Jawzat. So it's either, I guess, the shoulder of Jawzat or the hand of Jawzat. Okay, so we've gotten this far. Now, this then came into the Latin-speaking world, again, probably in the 12th century. And someone then saw it as Yad al-Jawzat. But the problem was, you see here there are two dots. But if we go back here, we'll see there are no dots here. So probably the dots were missing, and someone had to guess how to pronounce it. And how did they pronounce it? They didn't say Yad al-Jawzat. They took it with one dot, which then makes it read Bad al-Jawzat. And from Bad al-Jawzat, we then get Betelgeuse. So that's where Betelgeuse is several mistakes that finally lead to this name. Now, it even gets worse than that, because in the Renaissance, we have another way of explaining Bad al-Jawzat, and that was calling it Ibt al-Jawzat, because Bad al-Jawzat doesn't make much sense, but Ibt al-Jawzat makes a certain amount of sense because ibt means armpit. And so if you think of Betelgeuse as being the armpit of Orion, you can then sort of justify it. So we've gone from Betelgeuse to this new word, Ibtelgeuse. But notice that Bed and Ibt have no obvious connection, and especially if you know Arabic. But if you don't know Arabic, you might say Bed, but. It sort of sounds alike. So what we're dealing with, and I think what's interesting here, is that what we're dealing with is oral transmission. And the orality of this transmission leads to the interesting problem of how one interprets what one is hearing. So our first listener back at the court of Alfonso X, we think, probably heard bad instead of yad. And then later, someone wanted to interpret bad and said, well, that's probably Arabic ibt, even though we're now far removed from the original. Now, one last example here, and this is another star name, Cacaos. Now, this is a Byzantine Greek manuscript by someone named Gregory or George Chioniadis. And Chioniadis wrote a work called Schemata of the Stars, and it was written in the early 14th century. And he has a list of star names in this work. Now, the problem with this star name here, this Cacaos, I've transcribed it up there, is that it doesn't exist in any Ptolemaic star list. There's no Cacaos as a star. So this is again the result of another transmission error. This is due to an early copyist when transcribing the Arabic translation of Almagest star list. Now, there's a constellation called Cepheus, which we call Cepheus today, and it was no doubt transcribed as Cepheus. But now look up here, instead of one dot, we have two dots. So instead of Cepheus, which would have been correct, someone added an extra dot, or who knows, maybe it was a smudge. And so suddenly we have a new star called Cacaos, or actually, sorry, a new constellation called Cacaos due to one dot. Now, this leads us to an interesting question. You may be wondering at this point, why is some Byzantine scholar, who's actually from right here, it's okay if I call it Constantinople, why is he going to Iran to study Greek astronomy? An interesting problem, because was the center of science, especially at that period of time, the late 13th, early 14th century, in the city of Tabriz, especially under the Khanate of Ghazan Khan, the Mongol ruler at the time, who had converted to Islam. So Chioniadis travels from here, Constantinople, goes to Tabriz, and then he is seeking a tutor to teach him his own heritage, so to speak. And what it turns out that wasn't so easy to do. As we learned from one of a later Byzantine astronomer named George Chrysococcus, he tells us it was the rule with the Persians that all subjects were available to those who wished to study, except astronomy, which was for Persians only. He searched, meaning Chioniadis, searched for the cause, which was that a certain ancient opinion prevailed among them concerning the mathematical sciences, namely that their king will be overthrown by the Romans after consulting the practice of astronomy, whose foundation would first be taken from the Persians. Actually, it's a pretty good prediction, but anyway. So this then, getting back to Chioniadis, we're able to tell that this work, the schemata of the stars, actually is a kind of reworking of something by Nasiruddin Tusi that was written in Persian. So we know that Chioniadis was tutored in a Persian astronomy work and learned his Greek astronomy from a Persian in Tabriz who was teaching him this astronomical work by Tusi. So it's an extraordinary story if you think about it, because think about where he was coming from. He was coming from here, right here, well, not exactly here, but just down the street. There were Greek manuscripts. I mean, the guy knew Greek. There was an almagist in Greek, but there was no one to teach him. So he had to travel to Tabriz to be taught by Persians about his own, what we would call, one would think would be his own tradition. So this again gives us a sense of the complexities of transmission, and also why when we talk about rebirth, Renaissance, Western science, it breaks down when we have examples like this that show a very, what do we call it, complex way in which science of the ancients ended up getting into Europe. Now, don't want to take a lot more of your time. Just to give you an idea of the importance of this work by Chioniadis, it contains something in it that Tusi invented called the Tusi couple, which is a way to make straight line motion from two circular motions. This ends up appearing and is important in the work of Copernicus, and it seems likely that Copernicus might have seen the work of Chioniadis in the Vatican when he was there the Jubilee year of 1500. In that year, he was a kind of intern at the Vatican and would have had access to the library. And so we think this is one of the ways in which Copernicus might have learned of Tusi's work. Now, just very quickly, another aspect of this where we see the use of Copernicus has to do with the planetary models. This will show you how one goes from Ibn Shatir's 14th century model to the model in Copernicus's work, De Revolutionibus. They're virtually identical, except one is geocentric and one is heliocentric. This seems to have been transmitted to European astronomers by a Jewish scholar who had been at the court in the Ottoman court, someone by the name of Musa Galenos, Moses Gallieno in Hebrew. And we know through the recent work by Svi Langerman and Robert Morrison that Musa Galenos goes to the Venice region, and there he is presumably able to interact with Christian scholars, and we know that he was aware of Ibn Shatra's work. So this is another way in which we think the work of Ibn Shatra, in addition to Tusi, gets to Copernicus. So these examples could be multiplied quite a bit. For example, there are many cases of the Tusi couple in European sources before Copernicus. And there we find a number of Jewish authors who seem to straddle the divide between Islam and Christian Europe. This, for example, is Nicola Rem's 14th century version of the Tusi couple, which he may have well learned about from another someone living in France, Levi ben Gerson, Gersonides, who would have learned it probably through a trade route that went from Tabriz to the Alphonsine courts in Spain, and then on to southern France. So these, again, are these many examples that we can give show that there were very permeable borders in this period of time, so that knowledge could move quite easily from one area to another. So let me conclude. What are we to make of this disparate group of examples? One conclusion we might draw is that pre-modern scientists appropriated scientific material from other cultures and transformed these ideas, instruments, and theories, what have you, according to their own cultural needs and perspectives. But I think there's another lesson. No matter how peculiar the transmission of ideas may sometimes have been, and how misappropriation was definitely part of the process of scientific exchange, nevertheless, pre-modern scientists were able to actually appropriate and appreciate the ideas developed in other societies and contexts. I have mainly focused on the Mediterranean basin in this talk, but there are many other stories one can tell about exchanges between Christendom, the Islamic world, and South and East Asia. For example, here is the Tusi couple not going into Latin, but into Sanskrit through the work of a 16th century commentator named Abdul Ali al-Birjandi. His work, part of his work was translated a century or two later into Sanskrit. We also have an example of an Islamic map that seems to be partially reproduced in a Chinese schematic version from the 14th century. Again, these boundaries are not as hard and fast as we sometimes think of them. I think the transmission of ideas between human societies and cultures calls into question the attempts to analyze those cultures in terms of distinct mentalities. This can come in many forms, in other words, analyzing cultures by their mentalities, such as the insistence on treating local sciences through the methodology of anthropology, let's say. Of course, as we have seen, there are distinctive ways in which societies treat their scientific traditions, whether those are developed internally or appropriated from elsewhere. But if we insist to the exclusion of exchange on locality, microhistories, and mentalities, we are deprived of the longue durée of scientific traditions that spread from culture to culture. In fact, I would argue that human societies have been most vibrant, productive, and creative when they were willing to accommodate a diversity of ideas from whatever source and accept a variety of people within their domains. The cross-cultural transmission of ideas in the pre-modern period can teach us that our present is the fruit of many diverse cultures. And I believe our future should be as well. Thank you.
Well, thank you so much for this inspiring talk. Thank you so much. Yeah.
I can take questions if anyone has any.
So yes, now we can get some questions.
If there's time.
For our professor, yeah. Just we can have, yeah. I think, yeah, we have some questions. Maybe you can, yes.
Hi, my name is Mayuta. I'm a fifth-year PhD candidate at Rice University, and I'm really interested in studying the history of science and the exchanges of scientific ideas between, I would say, the Ottomans and the Latin West. And I really appreciate your conclusion. So first of all, I would like to use it in my dissertation, so you can quote your conclusion.
Thank you.
And the second thing, have you considered studying trade routes? Because in my research, I'm studying the exchange of astronomical ideas in the mid-17th century in response to the apparition of two consecutive comets. And I've actually discovered that the Dutch East India Company played a very important role in this process of the exchange or the transmission of objects. So did you consider looking further into trade routes?
Right.
The Venetians, for instance, were the lords of the sea.
Right.
So yeah, that's my question.
Well, there's an interesting book that I didn't write, but my colleague Robert Morrison has just finished, and it's about the routes between here, the Ottoman Empire, Crete, Cyprus, and Venice. This is my colleague Robert Morrison has just finished a book on this, so it will directly deal with your question, because he deals with trade routes, how shipping was done, how books managed to, let's say, get from here to Italy and so forth and so on. He's focusing on Jewish intermediaries, because Jews were able to go from the Ottoman Empire to the Christian world much more easily than Muslims could, let's say. So this probably would help. Another route that I think I just skipped over very quickly, and that is between the Mongols and, surprisingly, the Spanish kingdoms. I can show. I didn't want to overburden everyone with too many examples, but if you look at this is a very complicated proof of Euclid's fifth postulate, which has to do with parallel lines and whether they meet at infinity or not. This proof was originated probably in the Tabriz, Azerbaijan area of Iran in the 1290s. It, again, is quite complicated. It's part of a long tradition of trying to prove Euclid's fifth postulate. This ended up, the same proof is being discussed in a work by Levi Ben Gerson in Orange in southern France in 1320. So in 25 years from the time of its origination until it's being discussed by Levi Ben Gerson in France is 25 years. Now, Tabriz is way over here, Orange in France is way over here. It's the length and plus some of the Mediterranean in 25 years. Now, how was this facilitated? It's because of the relationship between the Mongols and between the Christian kingdoms, in part because the Mongols, before Ghazan Khan, had not converted to Islam. So the Ilkhanid dynasties were trying to figure out ways to circumvent, let's say, the Mamluks and other Muslim dynasties. So this relationship is, not only a trade relationship, but a very political, military relationship that's going on that helps explain how something like this could happen. So that's another of these interesting groups. You're absolutely right, though. That's the way in which one can begin to understand how these scientific ideas can move. They don't move on their own. There has to be human beings carrying them along. And those human beings are probably being facilitated by trade, by military alliances, by economic necessity. Yeah. Yeah. Yes, hi.
Thank you. Thank you, Professor Ragep, for your talk. I would like to actually ask for a clarification. So it's my understanding that actually you pointed out Plato emphasized, of course, the difference between world of appearance and world of forms and ideas, and hence maybe under the influence of Platonist philosophy in Greek, ancient Greek, maybe astronomy, they didn't really that much care about the correspondence between observations or perceptions and the science of astronomy. Whereas in the Islamic period, you point out or you suggest that also maybe thanks to Quranic encouragement that there are signs in nature, hence Muslim scholars maybe were more kind of sensitive about correspondence between their theoretical kind of astronomy and their own perception of what was going on. So I was actually curious whether how could a Platonist astronomy continue if you don't really take your observations seriously, and whether that was discussed.
Yeah, yeah.
Of course, if I correct understood your point.
Yeah. Well, you're asking a very good question, and since I'm not a philosopher, it's very difficult for me to answer. There are all these people here who know much better than I do. I would say it's an interesting question because we sometimes say, okay, Plato, Aristotle are translated into Arabic, and you have philosophers, Al-Kindi, Farabi, Ibn Sina, and they're part of this Hellenistic tradition. But there are major differences, and I think this is one of the things that is interesting when you look at something like a specific example, like this one of how you deal with astronomical observations or observations in general. There are very fundamental differences between someone like an Ibn Sina and a Plato. of course, this becomes very complicated because, you know, why does this come about and so forth? What is the role of Islam, especially Kalam, on these writers and so forth? And as I say, there are many people in this room who know better than I about these sorts of things. But I think it forces us to realize that we just can't call someone like Ibn Sina just a follower of Aristotle or a follower of Plato. Like, I don't understand, for example, someone will say, oh, Farabi is a Neoplatonist. But exactly what that means, when you take each example, it's always been difficult for me to see. So, you know, I'm just to agree with your point. I think it's a difficult problem, and you know, luckily there are a lot of good people who are working on it these days and trying to sort out these kind of questions. So, anyway. Okay, no more.
I think, yeah, I guess we don't have more questions, so
Okay.
thank you so much for
Thank
this
you.
great, inspired lecture, Professor.
Thank you.
So
Thank you. Thank you.
I would like to have you on stage for a moment, just to have a gift by a token of appreciation from our president.
Oh, thank you so much.
Take a
To shake it.
picture. Right.
Oh,
So
it's
this
beautiful.
tulip, Istanbul, and the university is hidden somewhere there, right? With the castle.
Oh, it's Rumeli Hisar.
So
Oh, beautiful.
we have our sign everywhere. right?
Thank you. And let me
Okay.
present you with.
So another print, the Istanbul Museum for the History of Science and Technology. Okay, okay. Let's we take
Okay.
this and
Well, this is we're practicing exchange.
okay, yeah. And we take a picture with this, right?
Yeah. Thank you. Thank you.
And this is a book by Professor Fuat Sezgin from the TÜBA chairman Muzaffer Şeker.
Oh, thank you.
Right. And,
Oh, thank you.
That is
Thank you very much.
his book anyway.
Thank you.
Thank you very much.
Thank you so
It was
much.
great.
Well, thank you very much for your interest in our lecture, and we look forward to seeing you in the other one, in the next one.
Thank you.